Welcome back to this class. In the previous class we have seen the unit number 12 in physical photochemistry about the Jablonski diagrams and various characteristics of the excited states of the molecules and its deactivation process as radiative transitions and radiationless transitions. In this session we will see the photochemical quenching of fluorescence by using the Stern-Volmer equations. This equations is actually a ratio of quantum efficiency of fluorescence in the presence of quencher and in the absence of the quencher. This shows psi f0 shows the quantum efficiency of fluorescence in the absence of the quencher. This is the psi f, it shows the quantum efficiency of the fluorescence in the presence of the quencher. This equation gives kf is the rate of fluorescence, sigma xi is the sum of the rate constants for all the unimolecular deactivation steps, and kq is the rate of quenching, q is the concentration of the quencher. This we have seen this. When you rearrange these equations, you will get Stern-Volmer as psi f0 by psi f is equal to 1 plus this is kq q and kf plus sigma ki. This equation kq by kf plus sigma ki will become ksv. ksv is the Stern-Volmer constant. This is used as the Stern-Volmer constant. It is the ratio of Stern-Volmer constant is a ratio of bimolecular quenching constant of the unimolecular decay constant. These are the unimolecular decay constant of kq and kf plus sigma ki. Is a ratio of the bimolecular quenching constant. It is called the quenching constant, unimolecular decay constant, and has the dimension. It has the dimensions of liter per mole, not the mole per liter. It has the dimensions of liter per mole. And KSV can be calculated from the plot of if is psi f0 by psi f versus the q. Q should be in the x-axis and psi f0 by psi f will be in the y-axis. It will give the positive slope, the one in the intercept. It will give the positive slope. From the intercept we can calculate the KSV. It has the unit of liter per mole. Now tau is equal to 1 by kf plus sigma ki. This is actually the lifetime of the fluorescent molecule. So in the absence of the bimolecular quenching, if there is no bimolecular quencher, it will represent the actual lifetime of the fluorescent molecule. So tau is the 1 by kf plus sigma ki. It is the actual lifetime of the fluorescent molecule in the absence of the quenching. Now we'll see the next very important thing, excimer and the excite plus. Excimer is actually a dimer molecule. It follows the act of the light absorptions. This can be represented as A star. This is an excited state molecule, forms a dimerization with the ground state molecule. This first dimers and then it goes on excitations. These are the two differences between the excimer and excite plus. First thing that now we have discussed here the difference between the excimer and the excite plus, that is excited state dimers. Excimer dissociate in the ground states, but excite plus stable in the ground state at room temperature, and the room temperature excite plus is more stable. It is the act of excimer is actually is formed after the excitations, act of light absorptions. After the light absorptions, it goes to the excited states and form dimers with the ground state A molecule to give a star. But the difference is in the excite plus, dimerization precedes the act of light absorptions. After the dimerization, it goes for an excitations. So it is after the dimerization it goes excitation, but here it goes excitation before the dimerization. These are the main difference. And the other difference is radioactive transition is very weak. In the excimer, radioactive transition is weak, but in the Exime Plus, radioactive transition is very strong. Radioactive transitions will be very strong here, and other is no absorption observed. That means it can further absorption is not possible here, but here in Exime Plus, intensity of the dimer absorption band is increases with the concentration. When you increase the concentration, the dimer's Exime Plus will absorb more, but here Eximer it will not absorb. It is no absorption is observed in the Eximer. The next main thing is emission characteristics of the normal things. Emission characteristics normal of the Eximer, but normally Exime Plus will not fluorescence, but the Eximer will fluorescence because already it is in the excited states. The broad structureless band is shifted to 6000 per centimeter to the red of the monomer fluorescence. Monomer means that is the A molecule. It is in the red side of the monomer, gives about 6000 per centimeter. It is about the Eximer. But the Exime Plus normally it will not fluoresce, but if fluoresces, it gives a sharp emission. Normally Exime Plus will not fluorescence. If it fluoresces, it will give a sharp emission on the long wave side of the corresponding dimer absorptions. Next thing is that emission is concentration dependent. Whenever it emits, it's dependent on the concentration of the Eximer, but it is usually independent of the concentration of the Exime Plus. Observed for this Eximer is generally observed for the planar aromatic hydrocarbons. It is only for the Eximer is observed for the planar aromatic hydrocarbons, but this is Exime Plus observed for ionic forms of Exime Plus is observed for the ionic forms of dyes in solvents in high dielectric constants. Solvent with high dielectric constants, Exime Plus will be observed. So these are the main difference between the Eximer and Exime Plus. Questions may be asked based on these questions and on the Stern-Wolmer constants equations. Some calculations have also been asked on the Stern-Wolmer equations. You will see about those things in the next section. Thank you.